Hello. This video is about basic facts on automorphism groups of fields and field extensions. The definitions are pretty generic and they work for rings or algebras just to set up the notations. Out of F, if F is a field, is the group of automorphisms. Of this field F. So it will be the group of all homomorphisms from F to F which are bijective, and for the case of a field it's enough to be injective or surjective. The first easy fact is that automorphisms of prime fields are trivial. Just to remind you, prime fields are those which are built out of 1 using addition and multiplication, and there are two distinctive classes: characteristic 0, which is a field of rational numbers, just a unique one in this characteristic 0 case, and characteristic finite, and there are many labeled by prime numbers, so they're integers mod p. In both cases, from the construction of them, it's easy to see that homomorphisms, bijective homomorphisms from a field Q to itself must be identical, and so is for the field of P elements. So the groups are trivial, just consist of the identity element. Moreover, if we look at an arbitrary field, then it has to contain one of those prime fields, and that is what is called a characteristic. If it contains a field of rational numbers, it is also called to have characteristic 0. Or it contains the field of P numbers, and then the characteristic of such F is called P. So in any of those cases, well, any field will have to be fitting one of those inclusions, having one of those prime subfields. So in any of those cases, any automorphism of the field F will not move around rational numbers. So it will be identical on rational numbers sitting inside F. And that is what is usually called the automorphisms of an extension of F extending Q. So by the definition, this group, if we have an extension, say F extending smaller field K, the automorphism group of this extension is just a subgroup of all automorphisms of F. So there will be some automorphisms, and the defining condition which we keep, which would allow us to keep automorphisms in this subgroup, is that the restriction to the subfield will be identical. So that is the automorphism group of the extension. And what we see almost immediately is, if we look at this extension of the prime subfield, then the automorphism group will be just all automorphisms. So this will be not a condition which it will be just coming for free. And the same in the finite characteristic case. Again, if we take any automorphism of such a field and we look at what happens with 1, it has to go to 1, and then all sums of 1 will have to go to themselves, will have to be stable. So the prime subfields are always fixed in the language of these automorphisms groups of extensions. We have all automorphisms being in this automorphism group of extension of the prime subfield. So all automorphisms fix prime subfields. Let me just write it in words. Automorphisms are identical on prime subfields. So that is really almost the same statement as just the fact that prime subfields don't have any symmetries. This is a useful notion, not just because of the fact that automorphisms are identical on prime subfields, but it is also useful in investigating relative symmetries, symmetries which fix a subfield. So the first fact, which is going to be very useful about such groups, well, it's a bound on their order. Let's write the order of this group, and the upper bound for that order is the degree of the extension. So this fact I will be deducing from another fact about algebras. So let me just put this technical fact here. If I have an algebra over a field F, and I will look at the set of all F algebra homomorphisms from A into F, then the number of elements, the cardinality of the set, should not be larger than the dimension of this algebra. So that, again, it's a very straightforward statement that will be implying this inequality. So let's see how it works. It's just one trick which allows us to do that. Let's take an automorphism, an element of this group of symmetries of the extension. Let's take an automorphism of F which fixes pointwise elements of the subfield K, and turn it into a homomorphism from a certain algebra. So the algebra which we'll be using is the tensor product of F with itself over K. It can be thought of as the result of extending scalars in F. So scalars originally are to be thought as elements of K, and then extending them from K to F as well. And it's easier to think in terms of tensor product rather. So that is an algebra, and then we can define, for any field, we can define a homomorphism from this algebra, so that the F tensor itself over K into F. So this will be considered as an algebra of F using, say, this first copy and multiplying, say, making it a vector space by multiplying with the first copy. And then considering it as an algebra over F, we will look at homomorphisms from this algebra into F. So that will be elements of they will be elements of this set, and then we will bound them by the dimension, which is exactly the same as the dimension of F over K as a vector space. So let me write what I just said. The dimension of A as a vector space over F. Now we can look at the extension of scalars. Picture of A, and then it's immediate that the dimension will not change when we extend scalars. So that is the easier answer for this dimension, for this side of the inequality, and that is the index. That's what we call the index. So the only bit which is missing now is take an automorphism, take an element in this group, and turn it into homomorphism from our algebra A into F. Well, here it is. Here's the recipe. So let's define this homomorphism on in decomposable tensor rather. Let's define it this way. Take x, take phi of y, and multiply them. So that is left to as an exercise to check that this is a homomorphism, additive, multiplicative, and moreover homomorphism of algebras. So scaling with elements of F by multiplying them with the first component in the tensor is going to be preserved, obviously. So all in all, it makes this assignment a homomorphism of algebras from A into F. So we count them. They are going to be as many as automorphisms of F over K at least, because any phi will give us such homomorphism and different phis will give us different homomorphisms, clearly. So that is the justification of the fact. And that is going to be very useful. Just as a preview, we are starting Galois theory, and this fact is really makes the definition of Galois extensions natural. So we always have this bound, and we just say that the extension is special when this bound saturates, and the name for this special is Galois. So we just say that field extension is Galois if it is maximally symmetric. We have as many automorphisms as only allowed there. So if the symmetry group of this extension is of the same order as the index. So that is, in my opinion, the most natural way of defining Galois extensions. Well, that is it for now. Speak later.